Okay guys, just to finish our talk about complex numbers, let's talk about complex polynomials, which we didn't get to in class today. But remember a couple of things about polynomials in general. If you know that z minus a, okay, using z as the variable, if z minus a is a factor, which means that it will divide into some sort of polynomial with respect to z. So z minus a is a factor. Then we know that a is a root. What does that mean? Well, that means if you put the value of a into the polynomial, it will equal 0. Now that has to do with the remainder theorem, which I'll talk about soon. But if we're talking about a polynomial again, and it has some complex zeros, therefore some complex polynomials, but the original polynomial has only real coefficients. So everything in front of the terms, if the coefficients are real, but there are complex zeros and therefore complex factors. So for example, if I'm talking about this thing, so I've got a polynomial, but this thing is a factor, z minus 3 plus I, just for example. Okay, well if that is a factor, remembering that, really I should change that into z minus brackets 3 minus I, then 3 minus I is 0, which means that if I put 3 minus I into the original polynomial, it would equal 0. The thing is, if the polynomial has only real coefficients, but it has a complex 0, like for example 3 minus I, then we would know, I would hope, that the conjugate of 3 minus I, we haven't mentioned conjugate at all this time. The conjugate of 3 minus I is also a 0. What is the conjugate of 3 minus I? 3 plus I. It is also a 0. And remember, they must come in pairs. So if you're told again, the polynomial has real coefficients. Now only if it has real coefficients, but it has a complex 0, then that 0's conjugate must also be 0. Now, this all comes back to the remainder theorem. Okay, very important for this thing. What do I mean by the remainder theorem? Well, the remainder theorem says that if I have an original polynomial, this time in terms of z, then I could write that in terms of, say, well, maybe some factors that are also polynomial. Maybe qz and whatever, tz, just for example. Now, if they are not true factors, then there might also be some sort of remainder with respect to z as well. Now, the remainder theorem says, that thing there represents the remainder. Just like if you take 10 and divide by 4, it goes in a certain number of times, but there will be some remainder as well. The same thing happens for polynomials. Now the remainder theorem says this: if you've got some polynomial, and in terms of qz, and one of those factors happens to be z minus a, and still say that there is a remainder with respect to z. The remainder theorem says that if you put the value of a into the polynomial, so the value of a is what you're putting into the polynomial, so you get q in terms of a, but z minus a will become a minus a, which becomes 0. Now, if that's the case, if you put a into a function, then this portion here would be equal to 0. So all you'd be left with is just a. So the value of a put into the original function equals the remainder. Now, if the remainder is equal to 0, then you know that z minus h is a true factor of the thing. So keep that in mind. If you put a value into a particular function and it doesn't equal 0, whatever that value is the remainder. If the remainder equals 0, then x minus a, you know, must be equal to, or must be a factor, and a must be 0. Just to finish with just an example, or maybe two. Say that I've got this polynomial, okay, z cubed plus 2z squared plus 5z plus 10. Now you could be asked to say, well, maybe this polynomial equals 0. Find the values of z. Or it might be just as simple as, well, not as simple, but it might be just asking you to find the factors of this particular. So factorize it. The first thing that you want to do is you want to look for values of z that you could put into this function polynomial to see where it equals 0. If you do that and it does equal 0, you know you have a 0 and you can find a factor from there. And you always go with, you do a bit of trial and error on values of the coefficient, values of the coefficient, I mean factors of the coefficient divided by the leading term. What do I mean by that? Well, not coefficient, the constant term is what I'm talking about. The constant term in this polynomial is 10. So you want to trial factors of 10, which will be plus or minus 1, plus or minus 2, anything else divide into 10, plus or minus 5. Divided by the coefficient of the coefficient in front of the leading term, which is 1 in front of the z cubed. So that would be just plus or minus 1. So it basically means you want to test into this polynomial plus or minus 1, plus or minus 2, plus or minus 5. Now it just so happens that I did some trial and error on this thing earlier, and when I put negative 2 into that polynomial, I get negative 2 squared, which is negative 8. Negative 2 cubed, which is negative 8. Negative 2 squared, which is 4, times by 2, which is 8. Negative 2 by 5 is negative 10. And plus 10, guess what? That equals 0. What does that mean? That means that negative 2 is 0. And therefore, it also means that z minus negative 2, or z plus 2 is a factor. Now, negative 2 is a real number. It's not a complex number. So you just can't say, well, the conjugate of negative 2 would be plus 2. It must be a factor as well. No, it doesn't work that way. Negative 2 is a factor. Now there's negative 2 is 0. There's 2 other zeros that we need to find in their factors. So this is where we start doing a bit of long division. We know that z plus 2 is a factor. So we're going to take z plus 2 and try and divide it into z cubed plus 2z plus 5z plus 10 and see how it goes. Do you remember how to do long division? I'm just going to pause this and do the long division and see what we end up with. So when I take z plus 2 and divide it into z cubed plus 2z squared plus 5z plus 10, I get it goes into z squared plus 5, no remainder. Okay? Always good practice to do your long division. So that means that my original function pz is equal to, it is equal to z plus 2, the original factor that I found, times by z squared plus 5, which is a quadratic, which means that I should be able to change it into 2 different functions. How do I do that? Well, I could use the quadratic formula negative b plus or minus the square root of b squared minus 4ac over 2a. Or I could get tricky and just say this. Okay, z squared plus 5. So if it was more of a quadratic, that's what you would use. The quadratic formula, negative b plus or minus the square root of b squared minus 4ac. But in this case, z squared plus 5, we could get tricky and say, well, z squared plus 5, that would be the same as minus 5 by I squared, would it not? Because I squared is 1, sorry, negative 1. Negative 1 by negative 5 will give you 5. I could be even a little more trickier and say that that 5 there, well, I could change that 5 into the square root of 5 squared. In fact, if I take root 5, I and square the whole thing, then I would end up with z squared plus 5. Now by doing that, I've changed it into a difference of 2 square rule, which is then handy because I can use the other side of the difference of 2 square rules, which says, if I look at z squared minus root 5I squared, I can change that into z minus root 5I, but also multiply that by z plus 5I. That makes 5I a root of this particular polynomial. Z minus 5I is a factor. What's the conjugate of 5I? Well, negative 5I. And if you go z minus negative 5I, this is where this other factor comes in, z plus 5I. 5I and negative 5I are conjugates of each other. So there's my polynomial, which I know it had 3 roots because it was degree 3 and 3 factors. There's the 3 factors. Z plus 2, which is a real, which includes a real 0, negative 2. And then 2 other ones, which, because they are complex, they must, the conjugates of themselves must also be zeros and therefore they're roots as well. Therefore factors as well. Alright, now just to finish with, this is haunted me because I forgot to mention it back when we first started talking about complex numbers. If, for example, I'm dividing by a complex number, let's just say 3 minus I, for example. 1 divided by 3 minus I. Okay, we need to work that out. Well, to get around that, what we do is, who remembers this? We take that and we multiply by the conjugate of 3 minus I, which is 3 plus I, over 3 plus I. Now 3 plus I over 3 plus I is equal to 1, so the value of this thing won't change. It will just be a different look on it. So on the top you've got 1 times by 3 plus I, which is 3 plus I. And on the bottom you've got 3 minus I by 3 plus I, which is the difference of 2 square rule again. That's the same as going 3 squared minus I squared. And of course we know that I squared is equal to 1. So this would become 3 squared, which is 9, plus 1, which is equal to 10. So you're left with 3 plus 9 over 10. Don't forget that. If you're faced with dividing by complex numbers, we use the conjugate to rationalize that quotient. Alright, thanks for listening, guys. Now, about the mock exam. You need to have your formula sheet with you, but not the calculator because we're doing Tech 3. Someone asked on the way out, what should you study? Well, somewhere between nothing at all, just take the night off, or everything that we've done in Specialist. Somewhere between those two extremes, and you'll be right. But don't worry, just try your best. Remember, if there's things that you can't do, well, you know you've got some time to work on that particular thing before the real thing, which is not till the end of week 4 of next term. That's a fair way away. But anyway, see you tomorrow. Have a good night. Thanks for listening.